The birth of aniline dyes. We're in the mid-1800s. Everything begins in 1856 when William Henry Perkin accidentally discovered the first synthetic dye, Methylene. This discovery launched the synthetic dye industry in Germany and Britain. Chemists rapidly began producing methylene blue, eosin, and various aniline derivatives. These dyes were initially for textiles, but physicians soon realized they selectively stained biological tissues. In the 1870s, Paul Ehrlich pioneered the use of aniline dyes in histology and hematology. Ehrlich discovered that acidic dyes stain basic biological structures, while basic dyes stain acidic biological structures. This concept, known as selective chemical affinity, is the foundation of Giemsa. In 1891, Dmitry Leonidovich Romanowsky made a key discovery. He combined methylene blue and eosin. Unexpectedly, he observed a distinctive purple coloration in malaria parasites, something neither dye produced alone. This became known as the Romanowsky effect. It turned out that oxidized derivatives of methylene blue azure dyes were forming complexes with eosin, producing intense chromatin staining. This was revolutionary for malaria diagnosis. In 1880, Charles Louis Alphonse Laverne first identified malaria parasites in blood. Later, Ronald Ross demonstrated mosquito transmission, but reliable staining was still inconsistent. By 1904, Gustav Giemsa, working at the Institute for Tropical Disease in Hamburg, refined Romanowsky's method. He standardized oxidation of methylene blue, stabilized azure dye production, optimized dye ratio, so how much of each to use, introduced glycerol and methanol for preservation. The result was a reproducible, stable stain suitable for tropical disease laboratories. This became known as Giemsa stain. Giemsa became dominant because it clearly differentiated malaria parasite chromatin, preserved red blood cell morphology, allowed parasite staging, worked in tropical climates, and had long shelf stability. And it wasn't just for malaria parasite. It also stained trypanosomes, leishmania, babesia, and blood leukocytes. In the 20th century, the World Health Organization standardized Giemsa staining protocols for malaria diagnosis. To this day, World Health Organization recommends Giemsa for malaria microscopy. It remains the gold standard in endemic regions. Even in the era of PCR and rapid diagnostic tests, Giemsa stained microscopy is still considered confirmatory. Giemsa staining is pH sensitive, and the optimal staining occurs at pH 7.2 buffered. So if the pH drifts and becomes too acidic, you get excessive eosin binding. Overly pink smear is the result. If it's too alkaline, you get excessive azure binding, and this is overly blue smear. This directly affects contrast between parasite and red blood cells and chromatin visibility. So for the diagnostic labs, they go for a 10% solution of this Giemsa stain. For the research laboratory, it's recommended that you use a 3% staining. And what you do is fix your slide with methanol. For rapid diagnosis in the laboratory, they usually do it for only a few seconds, but in the research setting, it's recommended you do it for like 30 seconds. I've seen protocols where they're routinely doing it for even up to 3 minutes, the fixation in methanol. Then you move to the Giemsa dye. This is where in the rapid setting, they're just putting it on 10% for 10 minutes. But in the research setting, they're going from 30 minutes to 45 minutes and even more. So that brings us to the end of this video. Thank you so much for checking out the video. I really appreciate you subscribing to our study group and giving the video a thumbs up. God bless.